Somewhere in Nara, there's a wooden tower that has been standing since the year 711. It has survived roughly 1,400 years of earthquakes in one of the most seismically violent countries on the planet. And here's the part that should not make sense. The pillar running through its center isn't attached to anything. It just sits there, loose, unbolted. In some versions of this design, it doesn't even touch the ground. It hangs from the top, swinging free like a plumb line inside a building that's supposed to be rigid. For most of architectural history, that would be called a flaw. In Japan, it's the reason the building never fell down. Fast forward to 1995. A different structure, a suspension bridge under construction over the Akashi Strait, its two towers, already standing nearly 300 meters tall, takes a direct hit from one of the most destructive earthquakes in the country's modern history. The epicenter is almost directly beneath it, and when engineers go back to measure the damage, they don't find a collapse. They find that the earthquake physically moved the two towers a meter farther apart than the blueprints called for, and instead of throwing out the plans, the builders simply finished the bridge to match what the earth had just done to it. That's not resilience by accident. That's a country that has spent centuries learning to build with catastrophe instead of against it. This is the story of how Japan turned earthquakes, typhoons, and one of the deadliest maritime disasters in its history into the reason it now has some of the safest, strangest, and most quietly brilliant engineering on the planet, and why almost none of it looks like what you'd expect safe to look like at all. Start with the puzzle nobody could solve for over 1,000 years, because it's the key that unlocks everything else in this story. Japan sits on the boundary of 4 tectonic plates. It absorbs roughly 1,500 noticeable earthquakes a year, and on average, several of magnitude 6 or greater every single decade. Any culture living on ground that unstable faces an obvious question almost immediately. How do you build something that lasts when the earth itself refuses to hold still? The 5-story pagoda at Horyuji Temple gave an answer so counterintuitive that structural engineers spent the better part of the 20th century trying to figure out why it actually worked. From the outside, the pagoda looks like a single, tall structure, 5 tiers stacked in careful proportion, each roof smaller than the one below it. But that's an illusion. Internally, the 5 stories aren't fastened to one another at all. They're stacked loosely, the way you'd stack 5 hats on top of each other rather than bolt 5 floors of a skyscraper into a single rigid column. And running up through the center of that stack is the Shinbashira, literally the heart pillar, a single core column that, in the most extreme versions of this design, isn't load-bearing at all. It simply rests on a foundation stone at the bottom, unattached to any of the floors around it, free to move independently of everything else in the building. When an earthquake hits, that independence becomes the entire point. The outer floors of the pagoda start to sway at one rhythm. The freestanding central pillar, unconnected to them, sways at a different rhythm entirely. The two motions collide out of sync with each other, and instead of amplifying the shaking, they cancel a portion of it out, roughly the same principle, scaled up into architecture, as two people on a seesaw finding a rhythm that stops the swinging rather than building it. Of the roughly 500 wooden pagodas built across Japan using some version of this principle, only 2 have ever collapsed in 14 centuries of recorded earthquake history. For a wooden structure with no steel reinforcement, standing in one of the most seismically active countries on Earth, that record isn't luck, it's proof of concept. For most of that 14 centuries, nobody could fully explain why it worked in scientific terms. Craftsmen passed the design down as tradition, generation to generation, the way you'd pass down a recipe rather than a formula. It wasn't until the second half of the 20th century that structural engineers, working with modern seismic modeling, finally confirmed what shrine carpenters had apparently understood by instinct and trial for over 1,000 years. The secret to surviving an earthquake isn't to become immovable. It's to stop fighting the movement and let different parts of the structure disagree with each other on purpose. That idea didn't stay locked inside temple architecture. In 2012, when Japan finished construction on the tallest tower in the country, the 634-meter Tokyo Skytree, Then, the tallest freestanding broadcasting structure on Earth, the engineering firm behind it looked past every contemporary skyscraper on the planet and went back to Horyuji for their answer. Running through the center of the Skytree is a 375-meter reinforced concrete cylinder, deliberately built without a rigid connection to the surrounding steel lattice tower around it. It's a modern Shinbashira, engineered from concrete and steel instead of cypress wood. Using oil dampers to fine-tune, ancient carpenters solved this with intuition and centuries of trial and error. Modern engineers solved it with simulation software and hydraulics. They arrived at the same principle from opposite directions across 1,300 years, which tells you something important about this entire country's relationship with disaster. Japan doesn't treat catastrophe as something to be resisted with brute strength. It treats it as a design problem to be studied, absorbed, and eventually turned into an advantage. Nowhere is that philosophy tested more directly than on the sea crossing between Kobe and Awaji Island, where Japan built what is still, to this day, one of the 2 longest suspension bridges ever constructed. The Akashi Strait is narrow, only about 4 kilometers across, but brutally unforgiving tidal currents, strong enough to reach 9 knots, one of the busiest shipping lanes on the planet running directly through it, and a seabed sitting in one of the most seismically volatile stretches of Japan's coastline. Engineers had been studying the feasibility of a bridge here since the 1950s, and when the technical committee finally reported back, their conclusion was blunt. This crossing would face design and construction conditions with, in their own words, no precedent anywhere else in the world's long-span bridge history. Construction finally began in 1988. 10 years of work, aimed at a central span nearly 2 kilometers long, roughly twice the length of any suspension bridge that had been built before it anywhere on the planet. Then, on the 17th of January 1995, at 5:46 inches the morning, the Great Hanshin earthquake struck. Magnitude 7.2. The epicenter sat almost directly between the bridge's 2 towers, which by that point had already been completed and stood nearly 300 meters above the strait. In Kobe itself, the earthquake killed more than 6,000 people and leveled entire neighborhoods. At the bridge site, engineers braced for the possibility that months or years of work had just been destroyed. What they found instead was stranger than destruction. The towers hadn't collapsed. They'd barely been damaged. But something in the ground itself had shifted. The 2 towers had been physically pushed apart, separated by a full extra meter beyond their original blueprint distance. Because the bridge deck hadn't been built yet, that shift wasn't a catastrophe. It was simply a new set of coordinates. Engineers absorbed the change directly into the final design, extending the central span from its originally planned 1,990 meters to 1,991 meters, and continued building on the earthquake's terms, rather than the blueprints. When the Akashi Kaikyo Bridge finally opened to traffic in April 1998, its towers stood equipped with massive tune-mass dampers, engineered to dissipate the energy of future earthquakes and typhoon-force winds designed to withstand magnitude 8.5 seismic events and gusts topping 280 kilometers an hour. For 24 years, until a bridge in Turkey edged it out in 2022, it held the record as the longest single span of any suspension bridge on Earth. It remains a structure that didn't just survive a major earthquake mid-construction. Earthquake edit its own design. That instinct absorbed the disaster, then build the next thing. Smarter shows up again in a very different form beneath the Tsugaru Strait, in a project born not from an earthquake but from a single night in 1954 that Japan has never fully stopped thinking about. On September 26th of that year, Typhoon Marie tore through the strait, separating the main island of Honshu from the northern island of Hokkaido. 5 ferries went down that night. 1,430 people died, one of the deadliest maritime disasters in Japan's modern history, and a tragedy that exposed, in the most brutal way possible, exactly how vulnerable the country's only connection between its 2 largest islands actually was. Ferries could be sunk by weather, a tunnel buried deep enough beneath the seabed, That single realization launched one of the most ambitious tunneling projects of the 20th century. Geological surveys began as early as 1946, but full-scale construction of the Seikan Tunnel didn't start until 1971, and it wouldn't finish for another 17 years. Engineers had to bore through volcanic rock, unstable seabed sediment, and a strait known for strong currents and near-constant seismic tremor, all while keeping seawater from flooding, a passage that in places runs 240 meters below sea level. It wasn't a controlled process. Water infiltration was a constant threat throughout construction, and cave-ins, flooding, and other accidents killed 34 workers before the tunnel was finished. When it finally opened in March of 1988, the Seikan Tunnel stretched 53.85 kilometers, 23.3 of them running directly beneath the seabed, making it, still today, the longest tunnel on Earth, with an undersea section and one of the deepest rail tunnels ever built. There's an odd postscript to this story that says something honest about the limits of even the most extraordinary engineering. By the time the tunnel opened, air travel between Honshu and Hokkaido had become fast and cheap enough that much of the original passenger demand the tunnel was built to serve had simply evaporated. Today, the Seikan Tunnel carries roughly 50 freight and Shinkansen trains a day rather than the volume of travelers originally projected for it. But that doesn't make the tunnel a failure. It makes it something more interesting, a piece of infrastructure built in direct, permanent response to a specific tragedy, engineered so thoroughly that it now quietly outlasts the very travel patterns it was designed around. The tunnel wasn't built to be popular. It was built so that 1,430 deaths in a single typhoon would never be allowed to happen to a crossing between these two islands again. And on that specific promise, it has never once failed. If the Seikan Tunnel represents Japan's answer to a single catastrophic night, the country's bullet train network represents something closer to a permanent, everyday negotiation with disaster, one that gets tested, without warning, dozens of times a decade. Since the first Shinkansen left Tokyo Station on the 1st of October 1964, just 9 days before the opening of the Tokyo Olympics, the network has carried more than 10 billion passengers across 60 years of continuous high-speed operation without a single passenger fatality caused by a derailment or collision. That record rests on more than good luck or careful scheduling. It rests on a specific piece of engineering most passengers never think about while they're staring out the window at Mount Fuji. A nationwide network of seismometers called the Urgent Earthquake Detection and Alarm System, or UREDAS. First installed on the Shinkansen line in 1992. Earthquakes travel in two waves. The first wave to arrive, the P wave, moves fast, but carries relatively low energy. It's essentially an early tremor, a warning shot. The second wave, the S wave, arrives seconds to tens of seconds later and carries the destructive shaking that actually causes damage. UREDAS was built specifically to exploit that gap. The moment its seismometers detect a P-wave signature consistent with a major earthquake, the system automatically cuts power to the overhead lines and triggers emergency braking on every train operating in the affected region. No driver input required, no human decision in the loop at all. Because the entire point of the system is that a human being couldn't react fast enough to matter. On the afternoon of the 11th of March 2011, that theoretical safeguard met the largest earthquake ever recorded in Japan's history. A seismometer near Kinkazen, operated by JR East, detected the initial P waves of the magnitude 9 Tohoku earthquake and sent an automatic stop signal to the Shinkansen power grid roughly 12 to 15 seconds before the earthquake's full force reached the surface. At that exact moment, 27 Shinkansen trains were operating in the affected region, several of them moving at speeds above 270 kilometers an hour. Every one of them received the automatic braking command. Every one of them came to a controlled stop. Not a single passenger was injured. Not a single train derailed while in operation. The earthquake that followed produced a tsunami that killed roughly 20,000 people along Japan's Pacific coast and triggered the Fukushima Daiichi nuclear disaster, one of the worst natural catastrophes in the country's modern history. And in the middle of that devastation, a piece of infrastructure carrying passengers at highway plus speeds did exactly what it was built to do, 12 seconds before anyone on board even knew something was wrong. It wasn't the first time the system had been tested under real conditions either. During the 2004 Chuetsu earthquake, a Shinkansen train actually derailed while running through the affected region, and even then, the early warning system had already begun slowing the train before the ground shook, and the train stayed upright with no injuries to passengers or crew. In 60 years of continuous operation across a country that averages several major earthquakes a decade, this remains the only Shinkansen derailment in the network's history, and even that single exception ended without a single person hurt. Earthquakes aren't the only disaster Japan has spent generations engineering around. "50 kilometers north of central Tokyo, buried 50 meters beneath a quiet stretch of Saitama Prefecture, sits a structure so enormous and so strange that visitors who descend into it often compare the experience to walking into a cathedral rather than a piece of civil infrastructure. Its official name is the Metropolitan Area Outer Underground Discharge Channel. Almost nobody calls it that. Most people call it G-Cans, or simply the Underground Temple, and the nickname isn't an exaggeration. At its core sits a pressure-adjusting water tank 177 meters long, 78 meters wide, and 25 meters tall, held up by 59 reinforced concrete pillars, each one weighing 500 tons and rising 18 meters into darkness, lit only by work lighting. 5 separate concrete silos, each 65 meters deep, are connected to that central chamber by more than 6 kilometers of tunnel running 50 meters below the surface, built specifically to catch the floodwaters that Tokyo's low-lying rivers can no longer contain during typhoon season. Built between 1992 and 2006 at a cost of roughly $2.6 billion. The system exists because Tokyo sits on ground low enough and rainfall in the region intense enough that ordinary drainage infrastructure simply couldn't keep pace with the volume of water a serious typhoon can dump on the city in a matter of hours. When a storm overwhelms the surrounding rivers, water is funneled through the tunnel network into the 5 collection silos, channeled into the central chamber, and then expelled through pumps powered by turbines adapted from Boeing 737 jet engines, discharging water into the Edo River at a combined rate of 200 cubic meters per second, enough to empty a full Olympic swimming pool in roughly 12 seconds. The system has been activated more than 150 times since it went into full operation, and in doing so, it's reduced flood damage in its protection zone by an estimated 90%. In August 2008, during the highest single inflow event on record, G-Cans diverted 11.72 million cubic meters of floodwater that would otherwise have poured directly into residential neighborhoods. And yet, almost none of the millions of people it protects will ever see it, because that's the quiet philosophy running underneath the entire project. Spend enormous sums building something citizens will never notice, so that the disaster it's designed to prevent never becomes a headline in the first place. That's really the thread connecting every structure on this list, whether it's 14 centuries old or barely 2 decades old. A pagoda in Nara that survives by refusing to be rigid. A bridge that let an earthquake rewrite its own blueprint mid-construction. A tunnel dug beneath a strait specifically because a typhoon once proved a ferry crossing wasn't safe enough. A train system that reacts to danger faster than any human driver ever could. An underground cathedral built purely so that a flood never gets the chance to become a tragedy. None of these were built to look impressive. Each one was built because something terrible had already happened, or was mathematically certain to happen eventually, and refusing to prepare for it was never treated as an option. That's the real difference between Japan's approach to engineering and the version most people picture when they hear the word engineering marvel. It isn't about building the biggest or the tallest or the most dramatic structure possible. It's about building things that are honest about the specific way the world is likely to try to destroy them. Earthquakes, typhoons, tsunamis, human error, and then designing directly into that threat instead of pretending it won't come. Go back to that wooden pillar in Nara one more time. It's still standing, more than 1,300 years after it was built. In a country that has since gone on to build a bridge that absorbed an earthquake mid-construction, a tunnel that answered a tragedy at sea, a train network that outruns its own catastrophes by 12 seconds, and an underground chamber built entirely to make sure a flood never becomes a headline. None of those newer structures were designed from scratch. Every one of them, in some quiet way, is still just that same freestanding pillar, swaying independently so the whole structure doesn't have to fall. The lesson sitting underneath all of it isn't really about concrete, or steel, or seismometers. It's about what a country chooses to do with its disasters after they happen, whether it buries the memory or builds the memory directly into the next thing it makes. So here's the question worth carrying with you after this ends. What does it say about a place that its greatest engineering achievements weren't built to impress anyone, but simply to make sure the last disaster never gets to repeat itself? This documentary draws on verified engineering, historical, and scientific reporting about real structures, events, and locations in Japan. No fictional characters have been introduced. All named projects, dates, and events are drawn from documented sources.